Everyone.
Professor,
Yes.
chapter test 3 is on 5 and 6, correct?
Yes. We had some
Yeah, because I
problems.
had this. I think you put the wrong test.
Yeah, some
Because-
students told me that yesterday. I fixed it last night. So it should be available again now. I've cleared the attempts that you've taken, and I made it now do Sunday instead of Wednesday.
Cool.
Also, Professor, there's like, when I took the test, it only had 2 questions on it.
Oh, have you taken it since last night?
Yes, the TO3 of the seeing it, the one that's for Sunday,
Right.
I only found 2 questions on it.
Okay, so that means something else is misbehaving now. All right, I will track that down and correct that after this class. So that again, y'all had till Sunday, but that'll erase the attempt that you've made since then. What happened is probably it didn't recognize the bank that I was using, which is weird. I don't know how that could happen, but I'll fix that too. Okay, but y'all have now until Sunday. Don't forget, and it's just chapters. It's technically 5 and 6, but you know all our chapters are somewhat comprehensive. All our tests are, so it'll be possibility of questions on those other things. But yeah, when you got all those astronomy related questions, they were not supposed to be there. It turns out 2 of my banks that I made for tests both start off with test 3, and I didn't realize that even though I'm in a non-astronomy class, it gives me access to all my banks. So I ended up pulling from a bank from an entirely different course, and it was the ending of it showed me it was an astronomy bank. So the last 6 questions were actually from astronomy, but the first 6, or excuse me, the first 1, 2, 3, 4 questions should have all been from the right area. But
Yeah, it was.
something wrong.
Also, to clarify, it's 10 questions total, right?
Yeah, it should be 6 and 4. Yeah, 4 conceptual questions and 6 calculational problems.
And Professor, how does it work if I've already used all 3 of my attempts for that test?
It's going to be entirely new test, so you will have no attempts yet.
Okay.
Okay. Yeah, I don't know how it ended up losing. If you said there's only 2, that means that, oh God, that's a mess. I don't know what happened, but somehow me copying it from one course to the other didn't pick up what it needed. So I will fix that, like I said, immediately after this class. Sorry about that, everyone. Damn it.
Thank you.
You're welcome. Sorry about it again. So anybody have any questions on any course material?
Can we go over some terminal velocity?
Yes. Yes. Okay. So the big deal with terminal velocity basically comes from that derivation that I did, which you can see on my YouTube channel. I don't know if I did one with this class, but the very last section in chapter, I think it was 5, we did a
6.
terminal. Is it 6? Okay. Thank you. We did a terminal velocity problem where basically we used a differential equation and we treated the air resistance as B times V. So I can do that again. For instance, let me give you an idea what that looks like. So basically what we've got is a body of mass M falling due to a force mg, but it's got acting on it a drag force B times V, which means, oh, that looks bad. Let's try this. Sometimes it focuses better when with an actual pin in the foreground. Yep, that did it. Okay. So we actually imagine the force of drag to be proportional to velocity. Another way that some people do it is force constant times V squared. But that's more with really thick fluids like through water and stuff like that, or at very high speeds, which may be more appropriate, for instance, for a car. But the summation of forces in the y direction equals mass times acceleration in the y direction. If I treat downward as positive y, then what I get is mg minus bv is equal to m dv dt. Okay. I can divide through by m if I so desire, and I'd get g minus b over mv is equal to dv dt. which I think you can see is dv over g minus b over m v is just equal to dt. And I integrate it from v equals 0 to v of t. Integrate this from t equals 0 to t. And that gives me, of course, I have to do a substitution. I'm going to say, let u be defined to be g minus b over mv, then du would equal negative b over m dv, or dv is equal to negative m over b du. So I'm going to use that way. I find it a little easier to do it that way sometimes. So I'll say negative m over b times the integral du over u is just equal to, this side just became t. So when I get this, I get negative m over b times the natural log of, now I'll put in my u, which would be g minus b over m v, evaluated from v equals 0 to v of t. That's all equal to just t. So now I can say, well, the ln of, I'm going to do g minus b over m times v of t over just plain g, because that's what happens when v equals 0, is equal to negative b over m times t. Now I raise e to the left-hand side's power, and I raise e to the right-hand side's power, and I assume they're going to be equal. That'll give me g minus b over m times v of t divided by just g is equal to e to the negative b over m t. Or we can go ahead and multiply through by g, and I'll get g minus b over m v of t is equal to g times e to the negative b over mt. If I pulled this over to this side and this over to this side, I'll get g times 1 minus e to the negative b over mt. Evidently some more people just came in. Let me let them in. And that's all equal to negative b over mv of t. So I'm really close. I can finally say v of, whoa, v of t is equal to negative mg over b times 1 minus e to the negative b over mt. So what that shows you is that basically, as this approaches infinity, this approaches 0. So the terminal velocity is just when mg is equal to basically b. Okay, that's more or less what's going on when the velocities, or excuse me, when mg is equal to b times v. That's the actual terminal velocity. So if you made a graph, for instance, of v as a function of time, so there's time, there's v of time. So at t equals 0, this is just 1. 1 minus 1 is 0. But it's going to go like this and sort of asymptotically approach why did it come out to be negative? Oh, that's right. I don't know why that negative came in, but either way, it's going to approach basically when mg is equal to bv, then that'll be a constant velocity basically. So v is going to approach mg over b. So that's what the terminal velocity is. You can just set mg equal to bv, solve for v, and that'll give you the terminal velocity. And that's asymptotically going to approach that. But in reality, it approaches it really, really quickly. So now, do you have a more specific question about terminal velocity that you would like to have some help on? Whoever asked, that is.
It was me who asked. Thank you.
Okay. That was sufficient, or do you think you need something else?
It was good. Just split it open into pieces that I can understand with through differential equations.
Yeah, it's just it's one of the easier differential equations. In fact, it's one of the first you'll learn in differential equations. It's called a separable differential equation, where you can just separate the dv over the dt and have a separate dv and a
Yeah.
separate dt.
And then you go into homogeneous and non-homogeneous and how to use it on that.
Right. What I'm bothered about is I probably made some kind of mistake somewhere, because that's not supposed to be a negative there. Oh, actually, I see. No, that doesn't work. I could pull this negative inside and make it e to the negative bt minus 1. That would probably work. But right now that negative is bothering me. But if I graphed it on Desmos, and that's what I'd recommend you do, just choose some constants for m, g, and b or whatever. And if I plot it on Desmos, I'm pretty sure it would look like this. But that negative is bothering me, so I might have made a boo-boo. I don't see the boo-boo, but I might have. So just be careful when you're trying to.
So how would you solve a problem like if they gave you just the velocity and just an acceleration? Because I saw that some of the ones on the practice test were giving problems like that.
Some of them they would give you the actual acceleration, or they give you what? No.
Like on some of them they just give you a velocity and a acceleration.
Oh, yeah. So they gave you like an
And then they ask you to
acceleration
find
as
on
a
a
function of
velocity.
time, and they gave you like some initial velocity or something.
I don't think they gave you velocity as a function of time. They just gave you an actual velocity value and an acceleration. Like they gave you an acceleration of 3 meters per second and a velocity of 20.
Okay. Well, that type of problem is something different. That's actually trying to get you to perform the same derivation I did when I said a was equal to a constant, and I set that constant equal to dv dt, and then I integrated it and got v equals v0 plus at. So there's some problems in there where they expect you to do that. And if you look in my YouTube channel, there's one where it says I'm answering a student question, and that's got that very problem worked out in it to some extent.
Okay.
Okay. Let me know if you can't find it. I'll pull it for you. Anything else, anyone?
I have one question.
Yes.
So when calculating the orbital period of a satellite or a planet, you get to the equation that is t equals the square root of r cubed over gm times 2 pi. I'm wondering how does that give seconds as a result? Because r, g, and m don't have seconds in their units.
Okay, so you're talking about basically the Kepler's law, third law thing. So
Yes,
let me refresh ourselves. So that's g m over r squared is equal to m v squared over r. Obviously that cancels out with that, but then v is equal to 2 pi r over t. This m cancels out with this m too, by the way. So I can plug this in, and all I have is v squared on this side. So I have g m over r equals 4 pi squared r squared over t squared. So t squared is equal to 4 pi squared over g m times r cubed. That's the one you're talking about, right?
yes, sir.
Okay. And you're wondering how you get seconds over here?
Yes, sir.
That's a good question. I'm glad someone's asking that. So let's look at right-hand side. From a unit standpoint, the right-hand side, 4 and pi have no units, but I have meters cubed, or let's do it as dimensions as opposed to, well, I'll do it as units instead of dimensions. I have meters cubed over. Now remember, G has Newton meters squared per kilogram squared. That's what the unit of G is. And then the unit of mass of the sun, for instance, is kilograms. So you can see now this kilogram is going to cancel out with one of these kilograms. And the other kilograms in the denominator. So I'm going to have meters cubed kilograms on top. And then I'll have Newton, which is a kilogram meter per second squared. And then I have times meters squared here. You can see this meter and these meters make a meter cubed. So that's going to cancel out with this meter cubed. And you can see this kilogram is going to cancel out with this kilogram. And all you're left with is a second squared in the denominator of the denominator. So that becomes second squared. So when you take the square root of t squared, you actually do get seconds.
Okay, that makes sense. I hadn't thought about splitting the newtons into its the base units.
Yeah, that's almost always the problem. Like when you get, if you took a chemistry course, you'd have these weird units coming up. It's almost always the problem that the Newton is a kilogram meter per second squared. That stumps you up. So you always try to get rid of that Newton first thing, because that's a big complex unit. Newton meter squared per kilogram squared. Good question, though. I'm glad you asked.
Thank you.
You're welcome. Anybody else?
I have some questions about the lab that I'm in, but I can wait till the end of class so that way the people who aren't in my lab
Okay.
don't have to. I don't
That
have to
sounds
wait.
good. Was it about the submit button? Because I did discover someone told me I didn't have a submit button on one of my labs.
It was there's a couple different ones. One of them was on the Excel lab. It says to print out the lab, and I can print them out, but I just took a snippet of the what it was asking for and just put that in there as a JPEG.
Yeah, there's no need to ever print anything out in my lab, even when the lab manual says it. I would much rather you just take a screenshot and embed it in the electronic document.
Okay, because that's what I did too.
Yeah, good. And by the way, I did confirm from the book, they did not get that negative in there. So I definitely made some kind of careless error with the negative. So you might want to check that out in this. They got exactly the same thing I did, except this is positive. So I made some careless mistake somewhere in this derivation. I just ain't seen what it is. Oh, I know exactly where it is. When I pulled this to this side, this was supposed to be positive. So correction. So that's what happened. Good. I already found the error. I hate it when I have an error floating around out there. All right. Everybody see what I had to correct? When I multiplied through by G, everything was fine when I had this over here. But what I then did is I pulled this over here and this became negative, but I forgot when I pulled this over here, it became positive. So that's where the sign was dropped. All right. So we finished chapter 5, which was on gravity. We finished chapter 6, which was on gravity. And now we're supposed to jump into chapter 7, which is on work. So I want to start off with a motivation or some kind of comparison to everyday life to make the concept of work make sense to what you know of as work in your everyday life. So what I'm going to use as an example is the same thing I've been using for a long time. Is I use basically the idea of mowing grass. Now, I realize a lot of families never made their child mow the grass. Some people grew up in apartments. Some people just didn't have their daughter cut grass. Some people don't have their daughter or their son cut grass. All sorts of neat stuff. But I think you can relate close enough to it because you've probably seen someone cutting grass. And what the deal is you normally have a lawnmower, and the lawnmower has this handle that comes up like this, and then a crossbar like this. And sometimes even got a little mechanism that you hold up so it automatically turns off if you let go of it. But the main thing is that handle is at some angle. And if you're, 6'2", 6'3", you can easily push that lawnmower just like this. Okay. And what they've done is they put that lawnmower handle at just the right angle and in just the right location where it doesn't cause the lawnmower to put too much weight on the front and too little on the back, or too much on the back or too much on the front. And that works just fine. But as a kid, when you're cutting the grass, you're not 6'3". Well, in most cases, right? When I started cutting grass, I was probably 10 or 11, and I was still quite kind of short. What I ever inevitably found myself doing is pushing forward on the lawnmower and literally leaning like this. And in other words, my body had figured out from a physics standpoint, even though I didn't recognize it at the time, that physically speaking, the most efficient way to push the mower is only apply a force directly parallel to the direction. Okay, that made sense, right? If you want something to go to the left, why are you going to push down or up? You really just want to push to the left, right? So that is a relevant thing to work. In other words, work, when you're doing it, is something I like to define work as the ability to drive a nail. Only it's got some caveats to it in that anything that can drive a nail should be considered work. And you got to consider the idea that the nail can be as small and as sharp as you want. And the thing into which it's being driven can be as stiff or as soft as you want. So it could be like, you know, really warm butter, trying to stab a finishing nail into a really warm butter. Okay. In other words, it doesn't take much of a force, but it takes a force and it requires to go some distance through it. In other words, and able to, or in an effort to actually push the nail in. So we need force and distance. In other words, that's one way of thinking about it. The other way of thinking about it is take that lawnmower, for instance, and you would probably say, hey, if let's say we're cutting the grass and we're running north to south. So my lawnmower's 24-inch blade is cutting a 24-inch wide swath, and I'm walking, say, 100 feet. And then I turn around, move the lawnmower one width over, and then walk south. And then turn around, move one width over, and walk north. And then turn around, do it again, keep on back and forth. Now, if it took me 100 of those trips, then that'd be, you know, a certain amount of work, not necessarily an amount that I could quantify. But if I cut another yard that instead of taking 100 walks, it took me 200 walks, I would probably conclude that that's about twice as much work as the first one. And in fact, if I found one that took 300 trips, 100 feet long, I would actually decide that that would probably be 3 times as much work as the first one. So from that, you might get the idea that maybe work depends on distance, right? Because it's really the number of 100 feet swaths that I cut gives you a basic distance. So that seems reasonable. Let's say work is directly related, meaning thumbs up, thumbs up. If the distance goes up, the work goes up. If the distance goes up by a factor of 10.75, then the work goes up by a factor of 10.75. That seems perfectly reasonable to me. So you would say F, or excuse me, work is proportional to D. And I'll show you that in a second. And then you might say, okay, well, wait a second. What if my pain in the butt little fat brother or sister or sibling or cousin is being a jerk and wants to sit on the lawnmower? Well, you don't necessarily want him to sit on the lawnmower because it's dangerous, but you kind of want him to sit on the lawnmower because he's a jerk and it's dangerous, right? Not only that, if he sits there long enough, the lawnmower's going to get hot enough to burn him. So yeah, it's win-win-win, right? So if your little cousin or brother or whatever decides he wants to sit on the lawnmower, I bet you would realize that that would be more work. Because before you had a lawnmower that maybe weighed, I don't know, 70 pounds, and rolling it didn't even require 70 pounds. You just had to push it with a force big enough to overcome the friction between it and the grass, and maybe the softness of the grass and all that good stuff. But now you're pushing that and your fat little brother, right? I think you would then realize that work is also thumbs up with the force you're doing, the force you're supplying to the system. Does that make sense? All right, so let's get a nailing on that. I'm going to nail that down by saying our first conclusion was that work should be proportional to, and that's the symbol we use for proportional to, distance. Okay, so if I pushed 100 feet times 100, that would basically be 10,000 feet that I walked. But if I did it times 200, that'd be 20,000 feet that I walked. Or if I did times 300, that would be actually I just forgot where I was. 300 times, that'd be 30,000 feet. Now that seems reasonable. That's the thumbs up, thumbs up. If you double the distance, you double the work. Now we also decided, since my fat brother rides on the mower, that it's also going to be proportional to the force you have to put into it. And that's actually a pretty good realization of work. But what we realize now is, going back to that original discussion, if I apply a force F and move a thing a distance D given by the vector D, then this angle theta right here being 0 lets me realize that this component of force right here is wasted. Right? that component does nothing. And in fact, you know from 2 chapters ago that this is actually going to increase the normal force. So I'll say plus the normal force increases, and friction is proportional to the normal force. So the friction is going to increase as well. So there's a lot of bad things about this component of force pointing downward. So we would like to ideally look for some way of only taking into account the part of force that's helpful, i.e. the force component that's parallel to the distance. Well, it turns out we've already created exactly that kind of function. It's called the dot product. So we can say work is equal to the force dotted with the distance vector, where the dot product, A dot B, make a prominent dot there, A dot B is defined to be, we want this really to give us, for instance, the component of F that's parallel to B. And you can see that if I take the F magnitude and multiply it by cosine theta, then that would be it. But then I'm only multiplying A by something, not B. So the definition is just A times cosine theta. That's the part that we really want. But since the B's there, we're going to put B's magnitude there as well. Of course, another way of writing that is just to remind you in vectors, this is the same thing as the magnitude of A, and this is the same thing as the magnitude of B, and then times the cosine of theta. But you can also see that it would be A component parallel to B times B, or you can also see, if you look a little closer, watch this, if I put A like this, and I put B like this, then I can take a component of A parallel and perpendicular to B by saying this is perpendicular. So this part would be A parallel, and this part would be A perpendicular. But I can also extend this line this way. And when I do that, I can say, okay, well, this is perpendicular to A. So this component right here would be B perpendicular to A. And this part right here would be B parallel to A. And actually, I've been writing just without the second letter, so I'll erase that. Okay. But since this angle theta is there, you can see that A parallel is clearly A times cosine theta. So that and that makes the A parallel. But looking at this bigger triangle, you can see that B times cosine theta is B parallel times A. So there's multiple different ways of writing this dot product. So the dot product can be the magnitude of A times the magnitude of B times the cosine of the angle between them. Notice there's two angles, by the way, between them. If you have A and B tail to tail, there's this one, and then there's this huge one. You always choose the small one, okay? So with that in mind, now you know you can multiply the magnitude of A times the magnitude of B times the cosine of the angle between them. So if you know all three of those things, or if you can compute the magnitude of A and can compute the magnitude of B, and you know the angle theta, then you can automatically calculate the A dot B. Or you can just, draw the parallel component, or luckily, a lot of times you'll look in the actual drawing that you're trying to analyze has the actual A parallel automatically there, okay? Now there's a nicer way of doing it. If you really just wanted the component of A parallel to B, there exists something called the projection. So the component vector parallel to B, but part of A is the projection of A onto B. Okay. So that's an actual vector. So I can put a vector symbol over it, and different books use different notations. This is the one I use. It may or may not be standardized. I'm really not sure, but I always make it up myself every time. What I always remember though is this subscript, which is the least important part. It's just the part that you're trying to match it up to. That one has the most occurrences. Because look, what I really want is just this part of A. That's all I want, but I want it in a vector because I got a vector symbol here. Well, I know that just this part of A is A cosine theta. So that's really what I want, is the A cosine theta. But I want to use it in a nice, neat formula. So I'll say A dot B, but then I realize, well, crap, that's too big by the magnitude of B. So I need to divide by the magnitude of B, right? But I also now see, well, that's a dot product, which is a scalar. This is also called the scalar product, by the way, and the inner product. Then I realized, well, wait a second, this is just a scalar divided by a number. I really want a vector. But I know the vector is supposed to be parallel to B, so I could just write B there. But then all of a sudden, I'm back up by a factor of B again. So this B down here didn't do me any good. So to get rid of that extra factor of B, I write B squared down here, and then I'm actually done. Because really what I'm doing is multiplying it by B hat. In other words, B divided by one of these B's is B hat. So that actually works as well. That's the projection of A onto B, and it's actually a vector formula, and it works nicely. Okay, so that's something extra you can use, and I use it a lot once I discovered it myself. If you wanted to know the projection of B onto A, then you do the same thing, but remember, this one's going to be the one that appears more often. So I'm going to say A dot B, and then I'm going to have to put A squared in the bottom and A up top, like that, and then that works as well. So those are both really valuable formulas. I don't care if you put them on your equation sheet or not, and they're really nice. It automatically gives you a brute force method to calculate a vector that is parallel to some vector B, but it's only the component of A that happens to be parallel to B. In other words, its length is right. So if I wanted just that little vector right there, that little, or excuse me, this little vector right here, A parallel, I would use this formula. If I wanted just this vector here, B parallel, I would use this formula. Okay, so that's sort of the neatness of the dot product. And as I said, I want to reiterate that this is called A dot B is the dot product. It's also called the scalar product. And it's also called the inner product. As you might suspect, there is also a vector product, which is the cross product we'll learn about later. There's also an outer product, which could be in terms of dyads or tensors and crazy stuff like that. But right now, all we need is a dot product, and we should recognize what it does. Is a dot product gives us the component of a vector parallel to another vector. That's partly what it does. It just picks off that component. So for instance, if you want to know that, for instance, the sunlight puts out 1,420 watts per square meter, and you've got the sun's rays coming in at, say, 70 degrees above horizontal, and then you have a window that's horizontal, you might want to know how much of that light is actually going to come into that window. Well, it can't be the full 1,420 because that would only occur if the window was exactly perpendicular to the rays of light. So what you do is you take the component of the rays of light that are in fact perpendicular to the window by taking a dot product, and that would give you the fraction of the 1,420 watts per square meter that goes through your window. That's in fact the amount of sunlight that bleaches out your clothing that you have hanging in your window, or your couch that you have under your window, or your dashboard that you have in your car windshield. It also can be used, and this is where I use it a lot, you can use it to actually find the angle between two vectors. A lot of cases, that's just stupidly simple. But when you start talking 3 dimensions, and you, for instance, know that the atoms in a lattice of atoms, which, you know, like a chunk of aluminum or something like that, you might want to know, well, how are the atoms oriented in that chunk of aluminum? Well, chunks of aluminum have one orientation. Chunks of iron might have a different orientation. Chunks of ice have an entirely different orientation. And in fact, if you want to know the bonding angles between two atoms, then you could use this dot product. But in order to do that, you've got to be able to solve for this, which means you need some other way of calculating a dot product. Okay, because this way requires you to know the magnitude of the vector, the magnitude of the other vector, and the cosine of the angle between them. If I had another way to calculate this, then I'd be golden. So that's what I'm going to introduce now. So let's say I take and write A dot B like this. I'm going to say A dot B is equal to AX I hat plus A sub Y J hat plus A sub Z K hat. That's just a generic vector with components AX, AY, and AZ. Now I'm going to dot product that with another generic vector, BX I hat plus BY J hat plus B Z K hat. Well, the dot product is a part of an algebra. It's actually a vector algebra. And it's part of an algebra. It actually obeys, I made a heart there for some reason. It actually obeys the principles of algebra that you're familiar with, like the commutative property, distributive property, the associative property, all those things. Well, with that, you can say, oh, well, the distributive property tells me that I just have to multiply this term by each one of those terms, and then this term by each one of them, and then this term by each one of them. So let's do that. I'm going to get AX I hat dotted with BX I hat. Then I'm going to get AX I hat dotted with BY J hat. Then I'm going to get AX I hat dotted with BZ K hat. Then I'm going to get AY J hat dotted with BX I hat plus AY J hat dotted with BY J hat plus AY, J hat dotted with BZ K hat plus AZ K hat dotted with BX I hat plus AZ K hat dotted with BY J hat plus AZ K hat dotted with BZ K hat. Now I'm going to use the fact that the dot product is what we call a linear operator. So this is a scalar times a vector, and this is a scalar times a vector. A linear operation allows you to pull the scalars out in front and just let the vectors do their thing. So in this case, I'm going to get let's take the first one. So in this first case, I'm going to get AX BX times I hat dot I hat. And then I'm going to get AX BY times I hat dot J hat. And then I'm going to get AX BZ I hat dot K hat plus AY BX times J hat dot I hat plus AY BY J hat dot J hat plus AY BZ J hat dot K hat. And then the last row, A Z B X K hat dot I hat plus A Z B Y K hat dot J hat plus A Z B Z K hat dot K hat. Well, actually, believe it or not, that's pretty simple, because remember, A dot B is defined to be the magnitude of A times the magnitude of B times the cosine of the angle between them. So what is the magnitude of I hat?
One.
And- Yeah, I think I heard somebody say it. 1. What about the other I hat? That's also 1. And what's the angle between I hat and I hat?
0.
0.
0. And of course, the cosine of 0 is equal to 1. So I hat dot I hat is just 1. And I think you can probably see that that's true for J hat dot J hat and also true for K hat dot K hat. That makes sense to everyone? Now check out what happens when you do I hat dot J hat. Well, that's still 1 times 1, but now it's cosine 90. And of course, the cosine of 90 is 0. And I think from symmetry, you can see that's also equal to J hat dot I hat. What about I hat dot K hat? The magnitudes are still 1. So it just becomes the cosine of 90 degrees. So you should get 0 again, which is also equal to K hat dot I hat. And what about J hat dot K hat? That's also equal to 0, which is also equal to K hat dot J hat. So in general, you can call I, this is what you might learn in a linear algebra course, that would be E1, and you call J E2, and you call K E3. But this would also work if you were like using spherical coordinates or anything like that. Then you'd have R hat, theta hat, and phi hat for spherical coordinates. But in doing that, there's a neat little formula that I like to use, and I'll just show it to you. It's not something you need to memorize or anything like that, but it's just kind of a neat way of expressing it. And that's E sub I, or let's do E sub M. E sub M dotted with E sub N is equal to the Kronecker delta M N. And you've probably seen this before. Let me say this is the Kronecker delta. It's a matrix that has 1, 0, 0, 0, 1, 0, 0, 0, 1. Y'all have seen that before. It's just the identity matrix, right? So what this is telling you is when you have I hat dot I hat or J hat dot J hat or K hat dot K hat, you get 1, which is that part. And if you have any of them that don't match, then you get zeros. So that's really all that means. Now, again, that was just a little extra stuff. But now that we understand what I hat dot I hat, J hat dot J hat, K hat dot K hat, and I hat dot J hat dot K hat, and all that stuff is, we can just go through one by one and realize this is 1, this is 0, this is 0, this is 0, this is 1, this is 0, this is 0, this is 0, and this is 1. So lo and behold, our formula that we're searching for is A dot B is actually AX BX plus AY BY plus AZ BZ. Now we have a really nice way we can calculate A dot B without having to use the angle between them. Since we have that and we have A dot B equals A times B times the cosine of the angle between them, we now can use A dot B to find the angle between these two vectors. For instance, the simplest case might be, let's do this one. Let's say this is our XY coordinate system. There's X, there's Y. And I'm going to draw one vector that is, let's say, over 4. So this will be 4 and up. Let's see, 1, 2, 3, and let's say up 3. So I'm going to say 1, 2, 3. And of course, you can tell the magnitude of that vector is clearly 5, right? And you might call this angle theta. Okay. Now let's draw another vector. And this one instead is going to be over 1, but up.
First, we can't see it.
Oh, sorry. Thank you. It's going to be over 1, but up by about 1.73, or the square root of 3. So this is that vector right here. So let's call this A, and let's call the blue one B. And this angle right here, we're going to call phi. Now, I bet you know enough about triangles to tell me what this angle is. Can anybody tell me what this angle is? Notice I went over 1, up the square root of 3, and of course, this would be a magnitude of 2. Anybody guess? I think I heard somebody say it. It's 60. You might have said 30, but you're on the right track. The main thing is, since the long side, square root of 3, is opposite it, you know it's got to be the big one. I bet you can all also tell me what theta is. Notice this is 4, this is 3, and of course that would be 5. So theta should be roughly 36.9 degrees. So you can tell the angle between them is about equal to 60 minus 36.9, which is 23.1 degrees roughly. I mean, we know this has a bunch more digits after the 0.9. So let's verify that we can actually use the dot product to calculate the angle between them. So first off, I'm going to calculate A dot B. So prove this. So A dot B is just equal to AX. So AX obviously has a component of 1 times BX. BX obviously has a component of 4 plus AY. AY has a component of 3, or has a magnitude of square root of 3. And then of course, BY has a magnitude of the number 3 itself. And then of course, neither one of them have a Z component. So we can see the result is 4 plus 3 roots of 3. Now we also know that A dot B is equal to the magnitude of A, which we can see is 2, times the magnitude of B, which we can see is 5, times the cosine of the angle between them, and that's what we're hypothesizing is 23.1. So we can now say that 4 plus 3 root 3 is equal to 10 times the cosine of theta. So theta equals the cosine inverse of 4 plus 3 root 3 over 10. So that's the cosine inverse of 4 plus 3 root 3, 4 plus 3 times square root of 3. That's equal to 9.196. over 10. So that actually gives us divided by 10. And now I'm going to take the cosine inverse of that. So I'm going to do cosine inverse of the answer I just got. And that gives me 23.1 degrees. QED. Okay. So you see the dot product is really good at determining the angle between. We knew that angle. That was a simple case. But if you're dealing with something complex, like let's say you had in 3 dimensions an atom here, an atom here, an atom here, and an atom here, but then you had another one where you came out the midway and came out midway here, because there's another one here, another one here. Let's see, this is like this, this is like this, this is like this. So if you came out halfway to here, and then halfway up here as well, and had that atom, you might want to know what the bonding angle is between this bond and this bond, right? If you, excuse me, I know that just fell out. So this is in the center of the cube. This is one of the edges of the cube. So it might help you to know what is the bond angle at this bond and what is the bond angle at that and how far apart they are. Well, that's where a dot product would be great. You use this vector pointing from the origin to the center of the cube and this vector pointing from the origin to the edge of the cube. And lo and behold, you could get exactly what that vector is, or excuse me, exactly what that angle is. So that's some of the stuff we can use the dot product for. Does that make sense to everyone?
Yes, sir.
Okay. So yeah, that's a nice, neat little thing about the dot product. We can think of it as something we can use to determine the component of a vector parallel to another vector. Or now that we have two ways of calculating, or multiple ways of calculating it, we can actually use it to determine the angle between any two vectors. And knowing that, I can't tell you how many problems have made themselves a lot easier to me, just because, like, I was doing a nasty statics problem one time, and I discovered the dot. I'd already learned that the dot product can give you the angles. And then there's this neat transformation thing that I learned in quantum mechanics, where you can multiply by a matrix if you want to switch a vector from one coordinate system to the other. So in trying to work out basically the ultimate torque that went through a series of shafts and U-joints, I used matrix multiplication and dot products and was able to get the answer in like half a page, where most people were doing like 3 pages worth of calculations. I did that in my first statics class, and my instructor asked me to be the grader for his tests, for his homework from there on out. So that was kind of cool. But anyways, that kind of stuff can come in really handy when you know it. If you don't know it, then you assume that it has no value whatsoever and you'll never use it. But hopefully now that you've seen some of the cool ramifications of using that, I think you'll use it more often. So back to work. What we found was that work is equal to F dot D, where F and D are vectors. Well, this is only true if F does not change along D. And that means basically the magnitude of F and the relative orientation of F relative to D have to be the same everywhere. Well, that's not always the case. For instance, you could do a plot of F versus X, just treating in one dimensions now, F versus X, then maybe the function does like this, meaning that when X is, say, X1, the force is quite small, but when you get to X is X2, the force is quite large, and then it levels off where it's about constant for X3 and X4, but then it starts to climb rapidly beyond that. That's just how the magnitudes are relating. The directions could change as well. So we have to generalize this, and what we generalize it to is work is equal to the work is equal to the integral of F dotted with DL, where DL is a little line segment along the path that you're going. So if you forget about this, even though I'm going to draw something that looks roughly like it, but if you imagine a line in space, and you consider this one point, which might have the value X, Y, Z, okay, the force might act this way. And of course, the DL is a tangent vector. So that should point parallel to that part of the curve right there. In other words, like the slope. And then you'd have to take the dot product of that. And that would just be for, point 1. And then, of course, point 2 would just be more or less X, Y, Z to X plus DX, Y plus DY, and Z plus DZ. And that would define a little interval right there. You could represent that differentially small interval by a vector that's parallel to it. and whose length is about that length. When you do that, then you can compute the work. Now, this is technically what's called a line integral. So there's some details you got to learn about it, and I'll sort of give those to you. But most of the time, you can quickly do the process without having to worry about it being a line integral. But what I mean by a line integral is you've got to sort of do something that evaluates f and dl specifically along that line. So sometimes you might have to make a parametric equation for the line or something like that. But most of the time in physics, it's just almost obvious. Okay. So let's look at a simple example. And this is the general case. So this is the absolute right formula. And this is often useful. In other words, we've learned when that's useful. It's when the f doesn't change with respect to d anywhere along it. Okay. But this is the more general case, the most helpful case. So for instance, if I wanted to say, back to our lawnmower problem, let's say F has a magnitude of 200.0 newtons. It's acting at approximately 37 degrees to the vector that describes the actual movement D, whose magnitude is equal to 100.0 meters. In this case, this is a constant force and it doesn't change anywhere along this. So I can use that other formula. I can use the simple formula, work equals F dot D. Okay. So F dot D means F times D times the cosine of the angle between them. So I know the magnitude of F is 200.0 newtons. I know the magnitude of D is 100.0 meters. And then I need to do cosine of the angle between them. Now, remember, I defined that angle in terms of them being tail to tail. So if you consider, took this vector and put it like this, then it'd be tail to tail. And you'd see that that angle right there is the exact same as that angle, because they're called vertical angles because they're across a vertex from each other. Okay, vertical angles, not because they have something to do with up and down, but because they're across a vertex from one another. So this one's 37 degrees as well, which you might recognize as being darn close to 36.9 degrees, isn't it? So if we use our 4, 3, 5 vector, this is about 37 degrees, then you can see the cosine of 37 should be 4/5. So if I multiply 200 times 4/5, basically a fourth of 200 is 50. Excuse me, 4/5. A fifth of 200 is 40. And then 5 times 40, or excuse me, 4 times 40 would be 80, right? 4 times, well, we'll work it out because I know when I do arithmetic in my head, things go bad. So I'm going to say 200 times 5 divided by 4. And of course I get 250. Whoa, that can't be it. Oh, no wonder I did 5 divided by 4 instead of 4 divided by 5. Idiot. That's what I was making a mistake with. So yeah, it's 4/5. So if I divide 20 by 5 or 200 by 5, remember 100 is 20s, fives, in other words, 20 nickels. So 200 would be 40 nickels. So I got 40 nickels. And then that's basically dividing by 5. Now I need to multiply those 40 nickels basically by 4. So that should give me the 160. So we could do 200 times the cosine of 36.9 degrees or 37 degrees if we want to. And we'd get roughly 160. And then times 100. And that gives me 16.00 times 10 to the third Newton meters. So that's how much work is done in pushing this object, whatever it may be, 100 meters this way while pushing downward at an angle at 37 degrees. Okay. Now that work could be done against friction, all sorts of stuff. And we could even calculate the work done by friction by realizing that the friction force is the force that's resisting its motion to go this way. And then you have like a cosine 180 thing. So you get a negative amount of work. And that would make sense because the friction is actually trying to stop the work. So that's another thing you can come up with. But that's a very simple, one of the simplest type examples to do. And actually the only thing that was ugly was watching my brain in real time trying to process the cosine of 37 degrees. But anyways, it did round to roughly 160. 200 times the cosine of 37 did round to roughly 160. And then 160 times 100 gave us 16.0 times 10 to the third. So that's a simple case. A more complex case would be an example where we're going to have a force that changes along the path of travel. So in this case, I'm going to introduce something called Hooke's law. And this is the same Hooke that I told you about when I introduced you to the history of Isaac Newton. Hooke's law basically says that whenever you apply a compressive force, let's say this finger here is applying a compressive force, this is just the earth holding the object up, and it might be a piling, for instance, then what's going to happen is this compressive force is going to cause this object to compress by a certain amount X. And what Hooke said was the compression X is going to be proportional to the force. So he said, at least the magnitudes gives you F is equal to some K times X. And it's also true for when you apply it in tension. So if I pulled to the right here, and this would be the earth just holding it, if I pulled to the right with a force F, I would tend to stretch this member and its length would change by an amount X, and that amount X is proportional to the force, meaning at least for certain ranges of forces, if I doubled the force, I would double this X. If I tripled the force, I would triple this X. Of course, you've seen before where metals will be pulled with such great a force that they throttle down, or they basically just shrink their radius really small, and they almost become like putty and just rip apart. Maybe you haven't seen that in steel, but you've probably seen it in other things that are a little less strong, like candles or pieces of plastic or something like that. Like you could take a comb and pull all the teeth off and give it a good yank, and if you can pull it hard enough, the main beam of the comb would neck down, get more narrow, and stretch and become really easy. That's when you've gone or long beyond their range of elasticity. So one of the things we do in physics is we study springs a lot. And in that case, you get a neat result where this works really, really well because the X is so large compared to the force. Because the spring is acting like a solid body, but it's meant to be stretched a long ways before it actually gets screwed up. In that case, we say F is equal to negative Kx. And you might wonder why that negative is there. This is the force provided by the spring. Okay, so let's imagine we set up a coordinate system where the x-axis is here and where the y-axis is here. And now we put a little mass on a spring like this. And over here is a wall that the spring is attached to. Okay. Well, if you provide a force on this, F2, what's going to happen is the spring is going to stretch and now this is going to be at X2. Okay, so you see what happened is X actually increased by me pulling to the right. The force on the spring, however, the force the spring is providing is pointing to the left. So that negative tells you which direction the spring pulls. So if you increase F, or excuse me, if you increase X, then F is going to increase in the opposite direction. If you decrease X, so you push it this way, then F is going to act in that direction. So that's the force provided by the spring. What we want to do is calculate the work done by F2. So what is the work done by F2? In other words, I'm doing just enough work to keep it moving until I get to this position X2. And this was originally at X1 equals 0. Then work is going to be equal to the integral of F dot DL. That's our formula. But as I told you before, this is a line integral. So you got to do certain things. What you got to do is you've got to decide when you get ready to do it, am I going to get DL to point the direction I'm going? Or am I going to get my range of integration to point the direction I'm going? So you've got to choose whether DL or range of integration is going to clarify the direction. Then the other will just be listed in the increasing coordinate direction. In other words, the default is always just use the coordinate direction. So if I go from X equals 0 to X equals X2, that's clearly in the positive direction. That is the positive coordinate direction. So if I chose to do DL and have it point in the direction of which we're going, then this one just has to be in the positive coordinate direction. However, if I use the range of integration to dictate which way I'm going, so I'd go from 0 to X2, then DL would just have to point in the positive coordinate direction. But you see in this case, both of them are right. Both of them are going to do the exact same thing. So this is one particular result that didn't really matter. That's why so many people can do this correctly, even though they don't realize they're doing a line integral, because you really got to screw up pretty bad before the line integralness of it bites you in the rear. So by doing this, I'm going to choose DL to give direction. So that's what I'm choosing. I'm choosing DL to be to point the direction I'm going. So I'm going to do just a X equals 0 to X2. Okay. That's just the positive coordinate direction. I didn't choose that because that was the way we go. I chose that because that's the positive coordinate direction. So F, of course, is going to be K times X, because that's the minimum it has to be able to overcome the spring force. And it's going to point in the I hat direction. And then the DL, of course, is just going to be DX, which also points in the I hat direction, because that's actually the direction I'm going. Okay. So what I get is, since it's a linear operator, we have K X dx I hat dot I hat, but I hat dot I hat is just 1, as we learned earlier. So I just get the integral from 0 to X2 of Kx. And of course, that's 1/2 Kx squared from 0 to x2, which equals 1/2 k x2 squared. So that's our work done. And that's actually a general formula. The work done in stretching a spring is equal to 1/2 k x squared, where x is the amount of stretch you used. Okay. Now, you might say, well, this seems like there's no case that would ever be a problem. Well, let me show you a case where it is a problem. If I did the same thing, only now I draw my coordinate system. Let's draw my coordinate system this way. And I take my box, which is right here, and my wall, which is right here. And now I move the spring to, or move the box to over here, which is negative x2, say. Now that spring has done that. Now the work is equal to the integral of f dot dl. And I'm going to choose dl to specify direction. So dl is going to equal negative dx I hat. Okay. So I get the integral of f is again going to be kx, but of course f is pointing that way, so it's going to be negative kx I hat dotted with negative dx I hat. Now I've chosen to make this the direction that we're going. That specifies it. So I've got to use the increasing coordinate direction for this. So I'm not going to go from 0 to negative x2 because that would be a decreasing coordinate direction. I've got to go from negative x2 to 0. So when I compute that, then I'd get negative times a negative is a positive. I get the integral negative x2 to 0 of kx squared, or excuse me, of kx dx, which equals 1/2 kx squared from 0 to negative x2, which in this case, it doesn't really matter because I'm going to have 0 squared 1/2 k times 0 squared minus 1/2 k times x negative x2 squared, which equals negative 1/2 k x2 squared. Okay. In other words, the negative in front of the x2 didn't cause this to be negative. It was actually the idea of subtraction. So in this case, what you're seeing is my force, which I applied this way, was actually pushing the thing this way and actually caused a negative amount of work to be done. So you can see that if you do things errantly, if I would have put 0 to x2 there, then I would have got a positive, which would have been the wrong answer. Any questions on that? So that's the big thing to deal with usually in line integrals is you got to let one of the things point the direction you're going, and the other thing just points in the positive coordinate direction. So you folks are free to go. If you have any questions, you can stick around and ask me. Other than that, I will see you next time.
Professor.
Thank you.
Thank you.
Yes, Thursday, Professor.
You too.
I had a couple more questions about lab if you have a second.
Yeah, no problem. Go over it, Dave.
So there's the
Dave,
go ahead.
what lab? Because I might have the same question.
What lab are you talking about, David?
Oh, physics lab 4. It's not actually on the lab itself. It's about like, for instance, on the lab 4, there's a discussion board that we're supposed to respond to.
Oh yeah, that's or is that the error propagation one?
Yes, sir.
Yeah.
Or not error propagation. It's the Excel lab.
Oh, okay, gotcha. Excel, I gotcha.
So far, from what I can see, I've been the only one that has responded to that.
Okay.
looking in the wrong spot, or?
Now you should be in the right spot. I didn't even remember putting that, but oh, I remember why, because you were the class that I didn't do a separate lab for that. I'll let you do it on your own. Did you have any questions? Because really other students are supposed to answer, but if they're not answering you, then I need to answer you. So if you posted a question, let me know, and I'll help you as best I can.
I didn't have any questions about it. I did post a reply talking about like something else I ran into with Excel at work that hopefully will be helpful to other
Oh, that's cool.
people. But part of the way you said how you're going to grade it is like 50 points for me putting a response out there, and the rest of the credit is coming from me responding to someone else.
Right.
So if someone else responds, like, do I not need to like?
Yeah, you don't have to reply if no one replies to you. I think I decided I was going to put some amount of points for people doing the actual discussion board. So you'll get those points, and other people will not.
Okay.
But it's like I said, it won't harm you because you didn't have any way of replying if they don't reply to you in the first place.
Okay. Cool.
I'll respond to your thing, David.
Okay, good.
Oh, thanks,
We
man.
still can help each
Yeah,
other.
so I'll get to it.
I have a quick question about test 3.
Yes.
So what I was saying earlier, there's only 2 questions. I only had access to 2 questions, but there's a total of 16 questions as well.
Well, that's weird. It should. I think I know where that could come from. No, that shouldn't be it. Oh yeah. Okay. So yeah, what happened is evidently when I created the correction, the one that was still there errantly was wrong. I don't know why your browser's not showing those other questions, but I will check and make sure that it's not a problem on my end. So within the next 30 minutes to 45 minutes, the test should be corrected, and you'll have yet another version up there, and I'll erase the old version.
Thank you, Professor.
Cool.
No problem. Sorry about that, Reese, and everybody else.
Not a big deal. And you said it's due on due Sunday?
Yes, the test is due on Sunday now instead of tonight, or instead of tomorrow night.
That works for me.
Good luck,
I have one
everyone.
question though.
Go for it.
On the questions where it's asking us to find the gravitational pull on each other, like they both have different, like say the sun and earth. How do you calculate? Do you find the separate gravitational pull and then subtract it by the smaller one?
Okay, so you're talking about like the difference in the pull from the sun to the earth versus the moon to the earth?
No. From the sun to the earth and earth to the sun, where they have 2 different gravitational.
Yeah, so the sun applies a force of gravity to the moon that's equal to G times the mass of the sun times the mass of the earth divided by the 1 astronomical unit squared in meters. The earth, according to Newton's 3rd law, applies the exact same force, but in the opposite direction.
Okay.
So that
And
the same magnitude, in other words.
And I think one of the questions asked, like, the reason why the moon stays so close to the earth is because the distance is closer, or is it because of something else?
The distance being closer is one part. The other part, of course, is also that, well, no, it has to be just that, because if you talk about the sun to the earth, the sun's mass is larger and the earth mass, of course, stays the same. But in the moon earth, it's the earth's mass, which the other one has, and the moon's mass. So that would actually cause a decrease. So yeah, I would say it's only because the distance between them is a lot closer.
Okay, just trying to make sure. Thank you, Professor. Have a good day.
Anybody else have any more questions? Otherwise, I'll say goodbye.
I've got a couple more questions real quick.
Go for it.
So for my lab, you said that lab 6 was due this Thursday. However, on the module section, lab 6 isn't listed there. Were you referring to week 6, lab 5?
That probably was what I was referring to.
Okay.
I said that. I'm not looking at it right now, so I could be wrong, but yeah, I think that should be what's going on. And if
Okay.
there's any confusion, I'll make it up on the day of the test and make sure y'all aren't screwed over by that.
Okay. And there's one other thing on my grades for this class, the lecture section. There's the chapter 6 homework. It says I have like a 15.78 in there, but if I go on the actual the Pearson, it says like a 98 or something %.
Okay, so that's a problem where it's going to update again. I've got to set it to automatic update, and it'll refresh itself eventually. But if you don't see it refresh itself by the end of the semester, make sure you let me know, because that's not the way it's supposed to happen.
Okay, cool. Thank you.
No problem. See you. Anybody else?
Yeah. I just got back in town like super late last night. From, I had to go to that funeral, and
Right.
dude, I didn't have any time to really get on top of my schoolwork. Is there any way I can get an extension on my chapter 6 homework?
Yeah, it's not a problem. Yeah, I'll go ahead and try to make that change now. That shouldn't be a big deal. Like I said, you did let me know everything, so I can fix that for you.
All right, sweet. I appreciate it. I really tried. Like, I'm not even gonna lie. Like, I was able to do the chapter 6 conceptual. But yeah, man, I
sometimes things like that happen, and I always give people extensions if they have a death in the family or something like that. It's no big deal for the homework standpoint to miss a little bit. So yeah, I will certainly grant you an extension.
all right, thank you. I appreciate it. And
Sunday, if that's okay.
say that again.
I said I'll probably just push off the deadline for you until Sunday or even Wednesday of next week.
Yeah, all I really need is like a day or two, because right now, like, I have all these other classes, and I had to schedule work. I'd work on one subject one day and the other subject the other day, and kind of balance myself out.
Right.
But everything's starting to come to a pinch point, and I'm trying to avoid it.
No problem.
And I want to deliver quality work. So yeah, that's kind of the deal right now. Also for your lab 4, I think it's Excel, right? So it shouldn't be difficult.
Yeah, it's pretty straightforward. Most people do that in like 30 minutes.
Yeah, because I did lab 5 like in class and turned it in. So it wasn't super difficult. So I'll get that done. I don't see myself having an issue with that. But yeah, if I could get an extension on chapter 6, that'd be great. I'd be
No
really
problem.
appreciated. Yep. Thank you so much. I appreciate you all working with me on this.
Super. Have a good one, son.
Yep. Thank you.
I don't know why I said son, but I did. Gerald, did you have anything? Otherwise, I'm gonna go ahead and close out. All right. I'm bothered by this negative sign on the work. I got to think about that a little bit. I did not expect that to come out negative, but anyways, keep that in mind when you're looking at this. Maybe I'd screwed up something. I don't know. I'll figure it out. Anyways, talk to you later, folks. Bye-bye.